really going to do 7,092 of these? I hope that that's your first question. And the answer is absolutely. Tune in. We're going to be doing this for decades. It's going to be great. Going to do one video for every stupid thing I've ever said. Alrighty. Intro to Tetra. This is Topple's next generation blockchain technology. And it is presented by Sean Cheatham. Don't trust that guy. He doesn't know what he's talking about. Unfortunately, he did write all the code that you're going to see today. So, whew, alrighty, let's get started. Oh my goodness, this is on StreamYard, and I got the other thing on my other monitor. This is going to throw me off so bad. I'm going to watch it over here. Okay, what is Tetra? It is a shape, or well, it's more of like a mathematical prefix for numbers and stuff. So there's like Mon or Mo, and then there's Dion or Dio, and then there's Tetra, and then there's stuff that comes after that. But yeah, so it is the successor to Dion. So yeah, it's the next upcoming major release of Bifrost. It's not out there yet. It's not production ready quite yet, but we're getting there. And it's our blockchain protocol implementation. Okay, so a blockchain protocol doesn't really do anything. It's just a protocol. You need to actually go and implement it, and that's what Bifrost does. So it's the code that runs the thing. And as I said, it's the successor to Dion. And Dion is the thing that is up in production, and it's live and running, and I don't know, it's up to like 2 million blocks or something. There's a lot of blocks. It's making a lot of blocks. Yeah, so eventually that's going to be replaced by Tetra. Now this one, Tetra was engineered like from scratch, and there was a very, very tight collaboration between the engineering team and the research team. So basically the folks that you saw in the the previous video. Basically every single day we meet up, we figure things out, we solve problems, and we write the protocol for Tetra. So it's an extremely tight collaboration. We verify the engineering work every day with the research team. Okay. This is so gonna throw me off where the slides are. Okay, so yeah, that's like what Tetra is. Now, why Tetra? Why did we do it? Well, it's efficient security combined with practical utility. Those are the two main motivators for Tetra. This little symbol in there. This little semi-group symbol. A little bit of foreshadowing for you. Yeah, so efficient security and practical utility. Now, on the efficient security side, we have Taktikos. Okay, so Tacticos, you've heard Aaron speak about it a few times previously. I'll show you where to find some more information, or to find his previous talks about it. I'll show that in a little bit. But this is basically it derives from Ouroboros, which is a proof of stake consensus algorithm. The difference, however, with Taktikos is that it acknowledges that physics exists and that it kind of causes some problems, namely in network delay. But I guess like in addition to network delay, you could also consider like CPU cost and whatnot. But I mean, for the most part, network delay, it takes time for these words that I'm speaking right now. You're going to hear these a few seconds later. Okay, so like networks can be slow. They tend to be really fast around like centralized locations, like central hubs, hotspots in cities and whatnot. Like AWS located like primarily in Virginia. So if you're in that area, you get really good speeds to like that particular data center. The thing is that we're dealing with blockchains here, and we need to assume that people are not locating their blockchain nodes in a centralized manner. And by assume, I mean we need to hope that users are not centralizing their nodes. Okay, we really, really want distribution like across the globe, for now, ideally across the universe. But for now, across the globe, which means remote locations, which means that we have a lot of network delay to contend with. Now, Taktikos, it considers this like as a first-class citizen within the protocol. So like that's very important. and it encodes it in the eligibility and leader election mechanism. Okay, so we get that security guarantee from Taktikos, like among other things. Again, go listen to Aaron's talks previously. They're really, really good, very informative, and they'll give you a lot more detail about the security mechanisms employed by Taktikos. Okay, so that's like the first big motivator. First major thing, like this is where we're introducing Taktikos, like bringing it out of research and bringing it into implementation. The second thing is application utility. Okay, so like something like Bitcoin employs what's called the UTxO model. So unspent transaction output. Each block contains several transactions, and those transactions produce outputs that can be spent by inputs of subsequent transactions. Now, those are unspent transaction outputs, and it's just like a simple cryptographic signing routine coupled with like a basic currency token. We want to extend that, however, with something called extended-UTxOs. So not only do we support like cryptographic signing routines, but we also support like a whole lot of other access control mechanisms. So you can lock up your data, for example, until like a later point in time. For example, once the height of the blockchain reaches 10,000, or you can compose that height lock with another cryptographic signing routine. So there's like a whole bunch of flexibility in what you can do with our blockchain as a user, like as a consumer of the data. Now that's on like the access control side, the proposition and proof side of things. There's also user-defined data. Okay, so in Bitcoin, you can really only deal with like the simple currency token, but in extended UTxOs, in particular, what we're trying to deliver in Tetra is a much more complicated like data model for the types of tokens that you can store, like the values that you can store on the chain. And now that corresponds a bit more with like the Topple Asset Management V2 specification that James has been speaking about. So that's that's still in development, in progress, but that is all like kind of part of the extended UTxO model that we're hoping to employ here. Okay, so those were like the two main like big feature motivators for Tetra. Now let's see, what's the next slide? What is Tetra? Okay, so I made this slide in like a few minutes, so it's not entirely accurate, but this is kind of just like a rough timeline of what has been developed so far in Tetra and what is still remaining to be developed in Tetra and when we hope to complete those things. So yeah, it's kind of just a rough estimate. Basically, a year ago, I think, is when we got started on trying to actually build this new major release. So that's when development really, really began. So about a year ago. The first thing that we tackled in the development process was establishing our types and our models and our schemes, or as well as scheme, whatever that is, the plural. We wanted to define these types ahead of time and really, think through what's like going to be encoded on our blockchain. What are like the first class data types that we're going to need to consider. Once we established those, we moved on to trying to implement consensus, and this is where we really tried to employ Taktikos. So this thing, the improved security model, and that's performed through consensus. And consensus, among like a few other things, is the leadership election process. So that's determining whether or not a block minter has the rights to produce a block at a specific point in time. And so again, I mentioned time there, and then previously I also mentioned physics, and we need to acknowledge that it exists and that network delay exists. So that's where we focused a lot of our attention early on, was trying to implement Taktikos. That was done through consensus. Another part of consensus was validating block headers. Okay, which is fun and all, but in order to validate block headers, you need to make block headers. And that's where we moved into block minting. So kind of the natural next step, once we established the rules for, a block header, we need to go and make block headers. So building from the first block in your blockchain, then you need to make the second block, and then the third block, and then the fourth block. Okay, so actually building these blocks is called the block minting process. And that process just assembles together a bunch of transactions and then applies, well, I mean, it builds the header. There's a whole lot involved in building the header. But yeah, it's building a header and then choosing the transactions to go along with it. Okay, so that's great. You got blocks and you can validate those blocks. But if it's like just me and I'm just running a node, that doesn't really do anyone any good. Well, I should say it doesn't do anyone else any good. You need peer-to-peer networking. Sharing is caring, right? Something like that. Well, we need to share those blocks that we just minted with the rest of the network. Okay, well, step one, we need to build a network. So that's where the peer-to-peer network comes into play. So we've got different peers. They're all running nodes, and we need to connect to them. Once we've established these connections, we need to go and share the blocks that we produce with those other nodes. And then, they accept those nodes, they validate them locally, and then they apply them to their chain. I guess that's kind of another mechanism that I didn't mention back here in consensus is, chain selection, or chain preference is another term that we like to choose. So when you have different peers all minting blocks at the same time, well, they're technically building different chains, different blockchains, and you need to choose which one is the best. Okay, so we've got peer-to-peer networking now. Peer-to-peer networking accept the blocks that are minted by the other nodes, and then we can validate them through the consensus process, and then we can also do chain selection through the consensus process. Okay, so up here at this point, I don't remember when this was. It was earlier this year is when we were doing peer-to-peer networking. So earlier in 2022. The next step is to actually make that blockchain useful for users. Okay, so everything up until now, up until early 2022, has just been establishing like the framework for associating headers to parent headers and like validating the logic and the eligibilities of those headers. To actually make a blockchain useful, though, that blockchain needs to incorporate transactions. So movement of funds. So for example, polys or arbits or ribbits, rest in peace, ribbits, or assets. Another factor at play is like registrations. So it's kind of another thing that I glossed over, and I'll continue to gloss over, but you also need to incorporate registration boxes into the protocol to allow new block minters to join and also contribute to the minting process. Okay, so the ledger is responsible for accepting transactions, validating the syntax of those transactions, validating those transactions actually spend funds that still exist and haven't already been spent. And also making sure that those transactions are properly authorized to spend those funds. And so again, that's kind of where this extended-UTxOs and application utility thing, those things come into play. Okay, so on-chain access control, well, that's handled by the ledger, making sure that proofs satisfy the propositions associated with all the transactions. And then the user-defined data for, well, that's where we're going to get into tokens and like fungibility and all that fun stuff. Stay tuned for that. That'll be, other broadcasts. Okay, so up until here, we're at the ledger. So we have transactions, we can add them to our system, and we can, calculate who has what funds. Awesome. Okay, but users still can't interact with our node quite yet. So that's why we need this thing called RPC, stands for Remote Procedure Call. And this just allows users to interact with the node. Okay, so like, a few months back, we were dealing with peer-to-peer networking earlier in the year, and that's where nodes talk to other nodes. But RPC is where users talk to the nodes. Okay, and we're employing technology called gRPC for Tetra, so that's another, difference in the Tetra world versus Dion, the predecessor. And so yeah, this just enables users to interact with the node, and it's what I'm like, I guess, actively working on right now. It's been a whole lot of fun defining the isomorphisms between the types that we defined here at the beginning in models and the types defined in our RPCs. So yeah, that's what I'm currently doing though. Okay, so that means that the rest of the stuff here, so delegation and rewards, node operational, did I spell that right? operationalization, and then the integration plan. It's like, how do we go from Dion to Tetra for the public network? It's like those things are, well, among the things that we still need to complete. And we hope to, accomplish those by the end of the year. Okay, so that's our timeline. And again, I did this in a few minutes, and I basically did it all from memory, which, well, what are we talking about again? Doesn't matter. Next slide. Okay, so how's Tetra? It's got a smiley face. It's happy. It's doing well enough. We can make blocks and everything. It's always fun. But I guess that really isn't how is Tetra. Really the title of this slide doesn't make sense. I just wanted to put a smiley face there. So, don't hate me for it. Anyway, the approach that we kind of took is to define a bunch of modular components. Okay, so we broke up like the different subsystems of a blockchain into different isolated components. Okay, so things like consensus, it's its own module. And it doesn't really overlap with the ledger, which is its own separate module, which doesn't really overlap with peer-to-peer networking, which is its own separate module, and then RPC, its own separate module. They're all decoupled libraries. But those decoupled libraries can be composed together, and they can serve like a variety of purposes. The most obvious purpose is to run a blockchain node. And so we have what's called the Tetra super demo, which, well, not only does it run a blockchain node, it actually runs multiple nodes in parallel, like all at the same time. So that's like, one purpose. Another purpose is to do like eligibility simulation for the purposes of like seeing if our configuration values in Tetra results in the same outputs that you would expect from like Prosomo or like the Taktikos research side of things. Okay, so we're able to like spin up a quick little test net using these decoupled libraries to like compute very specific values and then go and make sure that those values line up with what was designed and thought of in the research process. Okay, so that's kind of the composability there. Now, testable, this kind of, again, goes along with modular and composable. So testable is also super important. It's something that was kind of difficult in Dion. It's actually just difficult to do in blockchains in general. But like testing Tacticos in particular is extremely difficult because it is really hard to fake it. You can't lie to Tacticos. Aaron just won't let you do it. So making like fake data, fake valid chains is really hard to do. So testing things is really hard to do if your system is very coupled and not very modular. Like it's like serving a very, very specific purpose, because then testing requires you to make valid chains all over the place, which is something we unfortunately suffer from in Dion. So Tetra tries to take this as like, first class. It's something that we need to consider. So the modularity and then the composability lends itself to the testability of Tetra. Then again, the final note, algebraic design allows us to do all this testing in isolation without requiring that other parts of the system are, the true proper parts that would be running in a blockchain node. So that's how we did Tetra, or how we're doing Tetra, kind of like the style. Now, where is Tetra? The code for this, pretty much everything we do at Topple, or as much as we possibly can do at Topple, is open source. We want to make sure that, well, as much of the world as possible, as many eyes as possible can see our code and can audit our code and can criticize our code, or maybe with any luck complement our code and reference our code and reuse our code and build new blockchains or new technology with our code. Wouldn't that be awesome? But for the most part, it opens the door for criticism, which is extremely important in the blockchain space. We can't just assume everything that we do is perfect, unless I did it. So anyway, our repository is located at github.com/topple/Bifrost. And that has everything for Bifrost, including Dion. So if you're interested in the particular Tetra code, then you need to go to the branch just called Tetra. That's where I've been living for the last year and a half, or well, year, I guess, whatever the timeline said. So that's where you can find it if you're curious. We, of course, welcome contributions or ideas at any time. Okay, so the approach that we took, F underscores everywhere. It's yeah, if you've never seen it before, or maybe if you have seen it and, well, for example, if it were me 2 years ago and I saw this, I would hate it. But man, is it a lot more enjoyable to program in once you really get comfortable with it. Anyway, as I mentioned, we took an algebraic design approach. Basically, that means the abstraction of symbols. So define your symbols and then interpret them. We also took a functional style with Tetra. So that's abstractions of your computational model. And then finally, we employed tagless final, which is abstractions of context. Are these all the correct technical definitions of these three things? Absolutely not, but they all start with abstractions of, and then they have a third word in there, so it fit the pattern. So that's what I did, and it's close enough. So that's what I ran with here. So yeah, algebraic design. We define our symbols, and then we define the interpreters and what those symbols mean. So for example, if you have a data storage algebra, well, you could interpret that using an in-memory store, and you can interpret that using an on-disk persistent store. Okay, so you can just interpret your algebras in various ways. Functional style is abstractions of computation, at least in the quick little 3-word description I was able to come up with here. But really what I mean is you don't really care about the procedure that gets you to the result. You just care that something defines that procedure and you accept that as your argument. So you're just letting the computational logic exist somewhere else, which, okay, so that maybe that's not the best description because that exists in pretty much every flavor of programming, but again, it's like first class in functional programming is putting those functions, those computations, those unevaluated computations, as a first class citizen in the code. So it's it's just, I don't know, it's helpful and it's fun, and it makes me feel like a superior developer because functional programming, which no one does. I'm not actually a better developer. It's just no one does it, so I feel like I stand out more. So yeah, that's the functional style. And then the tagless final. This is, I guess, what I mean with those F underscores everywhere. Abstractions over the context. And really the most concrete case of this that I can think of is sometimes you need to interpret an algebra in an asynchronous manner. So you need to make an HTTP call, and that HTTP call is asynchronous and you get the result later. But sometimes you need to interpret an algebra in a synchronous manner where you get the result immediately. And if you want to put those two things in the same type interface, that's really tricky to do without something like tagless final, because then you can have your context be abstract. Is it a synchronous context or is it an asynchronous context? Don't know, don't care. We just abstract over that context. Okay, so these are kind of the three main things that I considered in the approach of the engineering of Tetra. All right, where are we in these slides? The tech stack. These aren't in a particular order, and it's also not a complete list. The ordering has to do with the color scheme of the gradient, and so gRPC and then the Akka logo really didn't look well in the bottom right. But because they're first, they look like they're the most important things. As far as this goes on this screen, the one in the middle, the Scala logo, is the most important thing. That's where we really, really embrace Scala in the Scala compiler in the Tetra code base. We lean on the compiler and the type system so heavily to well, make sure that what we do is correct. The compiler enforces a lot of things that you don't get in other languages, and those enforcements are really handy for blockchains that need to be correct, like necessarily. And so I guess it is super convenient that I clicked over on comments. What code does Topple code in, or is most commonly used? Well, in this particular case, we're talking about Scala. So that's the programming language. It, for the most part, runs on the JVM. Doesn't technically have to, but actually, yeah, I guess even in our case, it doesn't. It runs on Grail VM, which isn't technically the JVM. Yeah, so it's Scala. It's a functional object-oriented programming language. Yeah, it's awesome. Okay, so that's Scala. That's the language itself and the compiler that we use. The second most important thing is down in the bottom right, and that's the type level logo. And we in particular use a library called CATS, which I think is short for category theory for Scala. But basically, it replicates Haskell, which is another functional programming language. So it replicates a lot of the standard library from Haskell in Scala. And I'll get to why that's important in a little bit. But yeah, so it just really bolsters the functional programming aspect of Scala. Okay, and then I'd say like the third most important thing here is the Akka logo. So that's the blue wavy thing, bottom left. And in particular in Tetra, we're using Akka streams for some of the, well, I guess like a specific case that comes to mind is the block minting process, which is like necessarily asynchronous, but also time driven, and also like, I guess, linear driven and unbounded and never ending. So it's a good use case for Akka streams. Another good case is on our peer-to-peer networking layer. So I'll get to more details on that in a little bit, but we need to connect to peers, but we need to do a lot of different little things over that connection. So all of those little things that we need to do are called type protocols, and we run those within a multiplexer. And that multiplexer just allows us to run a bunch of little things over a single pipe. And that multiplexer is implemented using Akka streams and like an Akka graph stage, all kinds of fun stuff from Akka streams. And then the other thing that we use it for, which is a great segue, is for gRPC. So we use gRPC to like serve user requests or like client requests. In that gRPC, like all those RPCs, the remote procedure calls, are served over Akka HTTP. So that's, we kind of glue those two things together there. But really, like what I've aimed for in Tetra is to build a sort of a cohesive ecosystem between those four things on the left. And then finally, the other one is Excalidraw. It's not really in our tech stack, but I wanted to give it an honorable mention because it's where I spend a lot of my time diagramming and making a bunch of pictures. For example, this beautiful timeline was made in Excalidraw. Okay, so that is our tech stack. And then I think, let's see, what was I going to do next? Get to share my other window. I guess, well, so that's like the end of the slideshow here. I'm going to hop over to a browser to show some things there. Before I do, any questions? By any questions, I mean, I'm going to get some water. I'll be right back. Should have turned the music on before I left. It's okay, I'm back now. We're gonna groove for a bit. Give it a couple more seconds for some questions, see if they come in. Yeah, alrighty. Let's do some browser thingies. Tetra 4. Look at that. So that's where we are in our development. We're at 4, I think. But yeah, so here's Dion. Maybe this isn't the right list because I feel like we skipped something there. But yeah, so this is just kind of a little bit of explanation behind the naming. So numerical prefix here, if you're curious. Okay. Now, the code, I mentioned you can find it over here. Oh, yeah, so we got a clarification. It's platonic solids or hypercubes. That sounds more correct. I couldn't really think of that name. Anyway. Our code here, it's located at github.com/topple/bifrost. As I mentioned, if you want to see the Tetra specific code, you need to go to the Tetra branch. So that's located down here. You can drop down, search Tetra. And you can see this is, yeah, a whole lot of fun's been going on in here. Whole lot of folders too. So yeah, this is where you can find the code if you're curious. Okay, so talks a little bit about our tech stack, and I mentioned type level. We got Scala. And certainly, let me just close this here. We've got type level Scala, so CATS. CATS is a library which provides abstractions for functional programming in the Scala programming language. Okay, so Scala supports both object-oriented and functional programming, as I mentioned. And it's reflected in the hybrid approach of the standard library. But CATS strives to provide functional programming abstractions that are core, binary compatible, blah, 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 blah. It's just a really awesome library. See more motivation and whatnot here, but as I mentioned, it's a playful shortening of category theory. You don't need to know anything about category theory to use CATS. Okay, why the heck am I talking about all of this? This seems like rambling, right? And I'm just wasting time here. Well, there is a somewhat decent reason for it. Another language, as I mentioned, that employs a lot of category theory is Haskell. Okay, so this is just some documentation from Haskell standard library here. So they have something called a monoid in the standard library. So it's a type A is a monoid if it provides an associative function that lets you combine any two values of type A into one in a neutral element M empty such that, then blah, blah, blah. Now hop back over to CATS though. CATS also has a monoid. Monoid extends the power of semigroup by providing an additional empty value. Well, that sounds familiar, doesn't it? Point I'm trying to make here is that CATS, so this thing from type level for Scala, gives us a lot of the same programming style and thought process required for Haskell. Now, why is that important? Well, I guess I'll hop over here first. There's another repo up here on GitHub called Cardano Node. I don't know if you ever heard of Cardano, little blockchain. It's heckin' awesome though, because they kind of pioneered this thing called Ouroboros, which is, yeah, they say it right here, environmentally sustainable, verifiably secure proof of stake protocol with rigorous security guarantees. Okay, so this is what Tacticos is based on. So we get all the same guarantees of Ouroboros plus some other magic that's awesome. Anyway, Cardano employs Ouroboros for their network. And as I mentioned, Cardano is also awesome. Cardano is written in Haskell though, and we're written in Scala. But because of how much overlap there is, it just made sense to try to do some of the code base to be at least somewhat close to, how Cardano would do it for Ouroboros. A lot of the actual node that we the code that we care about, it's not really located here in this particular repository, but the code that we do care about is still written in Haskell. Anyway, there's a lot of overlap between the languages, if you're using cats. So those things combined, so cats gets us something that looks like Haskell, and then Cardano, which uses Ouroboros, is written in Haskell. So we just get a lot of overlap there. And it just makes it a little bit easier to follow how Cardano is implemented if we're doing something similar. Okay, so that was a lot of the motivation behind why we picked such this thing. All of this stuff: algebraic design, functional style, tagless final, and then the tech stack that we adopted. It was all just, it made perfect sense. I mean, that's kind of half of it. The other half is just that choosing a functional style it gives you a lot more rigor in your code. You can get a lot more guarantees out of it. It's a lot more safe that way. You can lean on your compiler a lot more, which I always love to do. Okie dokie. So yeah, that's Cardano, that's Ouroboros, proof of stake consensus algorithm that Taktikos is based on. I mentioned Taktikos, Taktikos proof of stake. So it's our blockchain's consensus algorithm. It's built from the foundation established by IOHK and Ouroboros Praus. If you want to learn more about it, you can, of course, go to this wiki page, wiki.topple.co, and then look for Taktikos proof of stake. Or you can go and watch Aaron talk about it here on YouTube. I think that you should be able to find what you need here, but so introducing Taktikos proof of stake. This was an awesome video here. You can go and learn more about it, where Aaron introduces Taktikos. You can also find the other videos in the series too. Anyway, Taktikos is the thing that we're trying to implement, the main thing that we're trying to implement in Tetra. So that's kind of why I'm harping on it so much here. Okay, so I'm going to pause one more time, see if there are any questions before I move on to some code and IntelliJ and the actual technical engineering that went into it. Alrighty, so looks like we got one question here. What was the hardest problem you've encountered over the last year? Well, this is an interesting one. So we can, of course, talk about the technical awesomeness of Taktikos, but I do want to. I'm always going to repeat this, but the awesomeness of the team that we have at Topple. Okay, so I'm Sean. I'm an engineer, and I think with my hands. I'm very tactile. I'm not a brain person. I don't think good. Luckily, we got Aaron on our team who does think good. He has good thoughts, really big thoughts. but they're like extremely formal, and like this is like academic work like that is very, very precise, and as I mentioned, formal. But I'm very informal, in case you couldn't tell. So I needed a translator. So someone really, really smart who could understand Aaron on the research side and could translate it into someone who does things with their hands like me. And that's where James came into play. Like, yeah, the person who asked the question, that's where you came into play. So the hardest problem for me personally was trying to distill Tacticos from a research protocol level and then engineer it. And luckily, we have a really great team at Topple. They were able to help me understand Tacticos and implement it properly. So, like, I don't know if that's really a problem. That's like just my personal problem that I've had to overcome, and I've had a lot of help doing that from the team here. Now, like, if I were to I'm trying to come up with like a technical problem that was like really difficult to solve over the last year, because I mean there were a whole lot of them. Tell you what, I'm gonna maybe I'll come back to this question because I'm gonna hop into the code next, and we'll be able to like maybe it'll refresh my memory on what was a real nightmare to solve. Okay, so IntelliJ. This is our build.sbt. Again, I'm on the Tetra branch that you saw from GitHub. Now, I mentioned one of the big motivators early on when started implementing Tetra was to go as modular as possible. Okay, so consensus and ledger and peer-to-peer networking, RPC, they're all decoupled libraries. Well, we can see that here in the build.sbt as well. I have a module called consensus. This handles consensus-related things. I've got a module called minting. This handles operations related to minting and producing new blocks. I've got a module called networking. This is a module for connecting to other peers and sharing information with them. I've got another module called ledger. This is for tracking state changes and like the impact of transactions, on the state. I've got a module called blockchain, which stitches all of those things together, and, forms them into, I guess as close as possible to a blockchain node. I've also got, Topple RPC. I've got, that's Dion technically. I've got Topple gRPC, which is the gRPC implementation. Then I've got crypto, which is like all the cryptographic routines. And in particular, one of the really cool ones is all the key evolving scheme from Aaron's work in Taktikos. So that's all that lives in crypto. I've got Cat's Akka. So again, we wanted a cohesive ecosystem between Scala and Cats and Akka. Akka coming from the Lightbend ecosystem. They don't play 100% nicely together right out of the box. They're not against each other or anything. It's just you need to do a couple extra things to glue them together. So that's what this Cat's Akka module does. Yeah, there's like a bunch of miscellaneous modules as well, and then the modules related to Dion. Okay, so this is kind of how it's broken down. It's very modular, and you can see it's a lot of folders. So sometimes it makes it hard to find things, but other times it actually makes it easier. Okay, so anyway, I mentioned in our timeline that we started with models. So I guess maybe I'll just start with going through some models here. And we're talking about a blockchain. What's the main primitive of a blockchain? Well, it's a block header. Don't worry about the V2. V2 means Tetra in this case. So when I say V2, I mean a Tetra block header. And you can see, oops, didn't mean to open that. You can see that it's very structural. We define very specific fields with very specific types, and in addition, very specific constraints around some of those types. So, for example, the metadata that gets stamped onto a block header can be at most 32 characters of Latin 1 data. Okay, so we use the type system and the compiler to really enforce certain constraints about our types here. You can also see there's really not much functionality. There aren't really any methods. Like I got, this one, I feel kind of bad about including it. But for the most part, all these models in here are just vanilla Scala case classes and sealed abstract classes. Our goal here was to just define a bunch of algebraic data types and serve them inside of a single library or like single package to reference for the core primitive types of our blockchain. Alrighty, so that's what models did. And then I'll briefly talk about type classes as well. So this is another important concept that it's part of the functional style that we employed. All of these models that we looked at are given functionality through type classes. Well, I mean, more than just functionality, I guess, but they're given properties and whatnot. You can kind of just see in some of the names here. So contains parent as a type class, indicating that some type T contains an optional reference to a parent. Well, in this case, a block header contains a parent because it references a parent. Need to fix some of these things. We don't use contains parents as far as I know, so I can get rid of it. Actually, a lot of these type classes we probably won't truly need at a protocol level, but they exist and they kind of just give functionality to the models. Okay, so that's what the type classes do. I'll also mention in our algebraic style, we have a module called algebras. And in this algebras module, we have some just basic shared interfaces that need to be used all throughout our blockchain. One of the most common is the clock. So in our particular flavor of proof of stake, based on Ouroboros, we have these things called slots. And a slot is a discrete unit of time that can roughly correspond back to like a normal clock that you're familiar with, like a normal timestamp. Anyway, I only mentioned that because these slots, these like discrete units of time, are very, very important to a lot of different places in our protocol. So they belong to this thing called a clock algebra, and this assists with things like scheduling certain things or determining which epoch you're in, for example. So this algebra, it just defines several different methods that don't have implementations. They're just abstract methods. And they also all return the same shape of result. So everything is in this F context. It's wrapped up in whatever this F happens to be. So for example, like an option or a try or a future or whatever it happens to be, some sort of container type. And this algebra, all of the methods all return the same container type, but of different values inside of them. Okay, then we need to take that algebra and go and interpret it. So we interpret this clock, for example, using actually, so it used to be interpreted using an Akka scheduler. So that's why it's named the the scheduler clock. That's just kind of left over. It used to be named the Akka scheduler clock, and then now it's just the scheduler clock. But really, it's just hooking into some of the type classes from Cat's Effect, namely the async type class, to help us with certain scheduling operations. But again, those technically, I have those implemented using the Akka actor system scheduler. So it's really using Akka at the end of the day anyway, but I'm using the Cats type classes. So that's, again, just kind of going back to, trying to unify the different libraries that we use from the different ecosystems. So Akka and Cats, mixing them together, and we are able to use them nicely throughout our Tetra implementation. Okay, so that's algebras and then some common interpreters that we need all over the place. Okay, so that was like for that was all roughly at the same time as models. Next up was consensus. And so that's where we have, this consensus library here. And I've got several algebras defined in here. We've got a block header validation algebra. This is responsible for validating some child block header against its parent block header. And then out comes either, a success or a failure. That's not the only responsibility of consensus. As you can see, there are a few different responsibilities of consensus, all kind of defined through algebras. So another responsibility is calculating the Eta value, and the Eta value is essentially just capturing, I guess, all the randomness encoded within an epoch. And so you need a calculation mechanism to determine that. So that's what this algebra is responsible for. Another responsibility is leader election. So determining if a minter is eligible to produce a block at a particular slot. So that's where the slot difference comes into play. It's also responsible for holding onto a local canonical chain. So what's the head of the blockchain? What is the current best block on the blockchain? And then these other two things at the bottom are, well, they're still important, but they're being replaced right now by dynamic consensus state mechanism. That's another important aspect of like Taktikos and Ouroboros, is like, how do you track the relative stake of the minters and who's registered and all that fun stuff. So all those things are within the domain of consensus. But I haven't included things that are, included in, so the next thing on our timeline, minting. So here in minting, we have another module. And this thing is responsible for, staking. So participating in the blockchain network, so you can stake funds, and your stake results in eligibilities, and those eligibilities allow you to produce blocks, and those blocks allow you to collect the fee rewards from all the transactions within the block, which allows you to benefit. So, that's the whole point of staking. That's the whole point of owning staking funds within the network, is so that you can gain rewards for them. Anyway, these are these symbols involved in staking. You need to know your address. You need to be able to determine an eligibility through the election process. And then you need to certify a particular block. Okay, so that's staking. Once you have like an eligibility, you need to use that to mint a new block. I guess that's kind of just captured in this block mint process. But we have an algebra which produces blocks. And then there's also a perpetual block mint, which again, just wanted to, going back to, mixing the ecosystems together. We're connecting all of the functional style from cats and like the algebraic design stuff with the streaming nature of Akka streams. So we do that here, and you're probably asking, well, why use Akka streams? Why not use, FS2 instead, which is another streaming library from the same folks behind cats? There's a good reason for that. I'll let you know when I think of it. Okay, so moving on though. We also have like leader election minting. That's like all kind of baked into minting and staking. Okay, so all of these things, they're within the domain of minting and producing new blocks. Okay, so back to our timeline. What did we do next? I forget. Peer-to-peer networking. Yeah, that's right. So this is where we have a module for networking. And again, this is built on Akka streams. One of the first things we needed was this thing called type protocols. Again, we kind of leveraged this similar concept from Cardano and how they do type protocols there. Type protocol, it's basically just a specialized state machine, but only one party has agency to send the next message in that state machine. And this is how two nodes are able to communicate over a very specific protocol, like a very specific data exchange. And you can run many of these typed protocols all at once, all in parallel, over this thing called a multiplexer. And again, this just stitches together multiple typed protocols into a single channel, and that single channel is used to communicate with a single remote peer. And then, well, so these packages, this type protocols, this peer-to-peer, and this multiplexer, these three packages are not specific to blockchains yet. They're completely generic, and if you could find another use case for them beyond blockchains, go for it. Our code's open source. But in our case, we do need to apply it to blockchains, so I just have another package here which, well, it does just that. It applies the blockchain domain to a multiplexer and a peer-to-peer network, and does all that stuff over type protocols. Okay, so all that stuff is for communication between different nodes in a network, and that's how we accomplish networking. Next up was the ledger, and let's see, starting to run out of time here, but that's okay because we're basically reaching where we are. So hopping back here, got another module for ledger. Somewhere, yeah. And so ledger is basically responsible for handling transactions. And in particular, validating those transactions against all of the previous transactions in the network. In addition, there's also the mempool, and the mempool is responsible for holding onto the set of unconfirmed transaction IDs. So things that haven't quite made it onto the blockchain yet, but will hopefully in the future. They sit in this mempool. And for now, that responsibility I've defined inside of the ledger. Okay, but then there's also all the validation stuff. So validating the syntax of a transaction, and then validating the semantics of a transaction, and then validating the authorization of a transaction. I guess it makes a bit more sense to see those as interpreters. So you can validate the syntax of a transaction. So making sure that the syntax actually spends something. So non-empty inputs. And then distinct inputs. So making sure that the transaction doesn't try to spend the same box more than once. And then maximum outputs. So making sure that you don't spend make sure that you don't try to create 1 billion outputs in your transaction, because that would cause problems. You need to validate against that. Then there's just like other syntax level validation checks that we need to perform. It doesn't require any other context of the blockchain to do these things, so that's why it's called transaction syntax validation, which extends a contextless validation. Semantic validation, on the other hand, does require some context. In particular, the context of all the transactions that have been included in the blockchain up to this validation point. And semantic validation is responsible for preventing double spends. Okay, so once a UTxO has been spent, well, it's no longer a UTxO because it's no longer unspent. It's just a spent transaction output, I guess. So yeah, this thing is just responsible for making sure that you don't double spend a box. Then finally, authorization validation. This is really, I guess, where we kind of hop back into why we did things. Well, application utility and extended UTxOs, and in particular on-chain access control, is all handled by transaction authorization validation. Okay, so validating that the proofs associated with the transaction input satisfy the proposition associated with that transaction input. And so that's authorization validation. Okay, and then let's see. Next was RPC, and so that's where we just did like some gRPCs. So topple gRPC. Got a protobuf Got a protobuf descriptor, which, I mean, for now it's kind of lightweight, but again, I'm actively building on this. So some of these things did not exist a few days ago, but now they do. But this is just how a user or a client would communicate with a node and get information from it. In particular, information that the blockchain node is good at handling or serving, which isn't everything. Got a different tool for that. Which means stay tuned. That's probably going to be in a broadcast at some point anyway. But this is our gRPC layer, and this is just how you can interact with a blockchain node. Why is this not compiling? Oh, it's because I was on a different branch that didn't have these things before. It's okay. It'll figure it out. I'm confident. It all compiled. Anyway, so that's that's like where we're at. We're like in the process of implementing the RPCs, and those will be useful for that other service that I mentioned, and like incorporating that data to make it usable for the users. And then we hope to eventually get to delegation rewards, and then the node node operations. It's way easier to say, and then the integration plan for how we're actually going to, well, let all you guys use Tetra. Alrighty. So that's that's pretty much all I got for today. That's part 0 of 7091. Definitely going to have 7091 of these. Absolutely. It's a lot of content. Any questions? It's a lot. I got a lot more detail to go to in part 1. That'll be fun. This is just the intro, though. It's been a lot of fun. Like this timeline here, I learned so much from August 2021 to today. Unfortunately, I still didn't learn how to speak. Goodness. These words are hard. Anyway, we've implemented a lot. We've got a little bit more to go. We're so close to the finish line. It's we did all of that stuff in that timeline with the tight collaboration between engineering and research. So I've had a lot of help along the way. I pressed the buttons, but other people on the team did all the thinking for me. So super appreciative of them. Okay. Well, I don't have anything else really for today. So I think, if we don't have any other questions, we could probably close out for now. So go ahead and throw this thingy up. Yeah, this thing. I don't know. Yeah, you guys can't hear, can you? Can y'all still hear me? Oh yeah, you can hear me. Nice, awesome. Okay, well yeah, there's the Linktree link right there, Linktree /Topple protocol, and you can find all of these links, including the link to watch the thing that you are watching on right now, including YouTube and Twitch and LinkedIn and all this other fun stuff. Yeah, so you can find all those links, like, subscribe, hit the notification bell, all those fun things. We'd really love to see you on Discord as well. If you got any questions, comments, criticisms, feedback, engage with us. We want to talk to you. Alrighty, that's all I got. Thanks so much, folks. Enjoy your Thursday.